Okay, so my name is Roy Arends. I work at Nominet. I know there's quite a few opinions out there about Nominet, but I work in the research department. So that said, I also just came back to work, having a very small addition to my family. So that means not a lot of sleep at night. So bear with me. Last thing I want to say: this is a live demo, so something will probably go wrong. Now. Also, I realized that I'm in between yourself and a beer, or actually, you are in between me and a beer, which would be very, very welcome. Anyway, what is Bumblebee? Bumblebee is basically a code name for a project we started a few years ago. The idea was we wanted to monitor DNS better. This is what we had at the time. We still have that. This is DSC. DSC is Domain Statistics Collector. I'm not going to click on anything further here. This is basically the state-of-the-art of free DNS monitoring software that you can get. Has been very, very useful in the past, but all it does is basically counting packets. We have built something completely different. What I'm doing is starting a bunch of JavaScript that's local. You can put it on the server somewhere. Let me just go to enter presentation mode. Should get rid of a few bars. There we are. New live. So what you're looking at is a bunch of dots. So that's it. Thank you. Good night. No. If you know a little bit about DNS, DNS is basically nothing else than a bunch of packets being sent back and forth, mostly over UDP, mostly very, very small. We monitor at the authoritative side. That means a DNS request comes in, hopefully a response comes back. We match that up and we store that locally for future reference. Every dot that you see here is an hour's worth of traffic. The size of the dot, naturally, is the volume of traffic within that hour. And the color of the dot is the ratio between things that exist. For instance, example.co.uk is a domain that exists. And everything else. And that includes domains that do not exist. For instance, example.uk does not exist. Also things like refused. If you ask us something for .info or .com, we're not authoritative for that, so we will respond with refused. The ratio basically means if it's green, it's good. Most of the things queried within that hour does exist, and if it's more towards red, that means there are some issues there. It might not exist. We might see a lot of load with refused, etc., etc. I'm also going to touch upon bind a little bit. Now, at Nominet, we're very, very big fans of bind. We run bind. We've done it for a very long time. We're big fans of ISC as well. In the abstract, we mentioned bugs in bind. There's actually one bug we want to mention. In 2011, has been fixed for a long time. We can all move on from that. But the reason we mention it here is because we've used this tool to find it. First, a little bit more about the tool itself. You can actually, if this would be a touchscreen, it isn't. I can touch it, but it doesn't mean anything happens. If this would be a touchscreen, I could touch by hand every individual dot here. I can select multiple dots or multiple days, basically. I can select here a single day. Now, obviously, nothing much happens, but I can add a few windows. Like in DNS, you have queue types. You can ask for an address. You can ask for a mail address, which is an MX record, basically. We group those together in this little window. You see type A, type PTR, type MX. I can also show the responses that those requests got. And I can click here on R code, and I get that too. And this is basically a day's worth of traffic, January the 5th, 2015. It is fairly real time. It's not real time. What I mean with fairly real time, I think, and I'm looking at Ray Bellis over there, who did most of the development work. You all know Ray Bellis. I think he's part of the board here. If that makes any sense. Sorry. Program committee. Sorry. I am Dutch, so I often go to the Dutch equivalent of a network operators forum. This is my first UKNOF, so I apologize if I got anything wrong. as I said, Ray did most of the work, so I'm looking at Ray if I do something, if I say something wrong here. Now, there's about a minute delay. So when something happens now, we can see it in our system about a minute or 70 seconds later, something like that. So this is how real time it is. I've selected a day's worth of traffic. There's quite an interesting interaction here. I can move this along. I can zoom in and zoom out. This is zooming out, of course. I can go back to several days. I can go back to several months this way. I can go back to several years, if that makes any sense. If I, for instance, check on things like IPv6, I understand from today that people are interested in IPv6 as well. So let me show IPv6 here. There we are. This is the ratio between IPv4 and IPv6, or not the ratio, this is the amount of traffic we see of IPv4 and IPv6. Let me get rid of the other screens here. I can increase the granularity at will. Now it's default 960 minutes. I can graph it by second, but it would be a very dense graph because I've got here multiple weeks basically. But if I can, I'm going to try something live. Here I can show several years worth of traffic, and I can see the increase over IPv6 if I'm interested in that. There's an awful lot of data going back and forth now. You see those flappy wings? It's all in the sense of Bumblebee. We have a queen, we have a hive, and of course, we didn't know that at the time, but bumblebees do not have hives. Bumblebee live in mud or in holes, but not in hives. Honeybees do, but bumblebees not. I'm sure you're waiting for that kind of information. Anyway, this is several years. I think it's about 2 years worth of information. I can select this. I can see Ray cringe now when I select this dot and then select this dot over there. Sorry?
What time is this planned to finish?
Well, this should be a few seconds. This should be fairly quick. Yeah.
Not sweating at all.
So, if I'm going to deselect IPv4 here. You see a nice increase over IPv4. There's, of course, an enormous amount of noise in the end. This is because of, I'm just going to call it out, I don't care at this moment. OVH is a French company. They have a few customers who are doing awful things. They think they cannot be detected by doing things over IPv6, but they can, and we see it, and we're suffering from it. Not that much, but that's why you see an enormous increase in IPv6. We know exactly who does what there. So it's not that we're not doing anything about it, but this kind of messes with the data, if that makes any sense. So IPv6, you see a nice, fairly slow, but a nice increase of traffic. Now, it doesn't mean that there's more deployment of IPv6 or more variety of IPv6 or different addresses of IPv6. It just means we see more traffic coming over IPv6. Excuse me. We can do the same thing for DNSSEC. Looking at Ray again. Yeah? So we can see a similar increase in DNSSEC. In a minute, I'll go and explain a little bit more about the backend and stuff. Initially, we thought of using things like Cassandra and Hadoop, and both of these things are great, but they were great for unstructured kind of data. Sorry, DNSSEC is back, and we also see a nice increase of the use of DNSSEC. Total packets.
See on the bottom of that window, that's actually a graph, 400 billion packets.
Yeah.
Which just returned about 15 seconds.
Yeah, this is about 400 gigapacket, and this is also how fast the backend system is. We do a lot of tricks, we do a lot of optimizations there. Yeah, it is pretty fast. The reason we want it so fast is well, I don't know if you know things like BI, business intelligence from Oracle. We have systems that work on BI. It's great stuff if you know how to use it. The problem there is you think of a query that you want to do. You type in that query, you make some coffee, and then you realize that something was wrong in the query. You didn't include, for instance, everything with the RD bit, if that makes any sense to you. If you're a DNS guy, you know what RD bit means. And so you have to redo everything over again, and then you're stuck with a bunch of data that you now need to graph. That the whole process requires a few things. You need to know databases, you need to know DNS, you need to understand how to graph data. You need to be able to structure data in a sane way, and then you still cannot interact with it. We try to solve it with this little tool, and we have kind of solved it. We've put some non-DNS folks, some non-database folks, some non-network folk behind this tool, and it is pretty easy to see trends and patterns and statistics this way. I'll show you something in a minute that should be immediately obvious that something is wrong, even though you might not know anything about DNS or networks in general. Where was I? Oh yeah, that one bug in bind. Sorry, ISC folks, I'm gonna show that now. Won't reveal too much of it. But before I do, I want to show you how fast filtering is. I can filter on basically anything I like. Let me go back to 21 days. That's because I know what's about to happen there. I can set, for instance, things with the RD bit set, right? And there it is. We receive between 3 and 5 billion DNS requests per day. This is over a set of, I think, 11 or 12 systems, nodes, if you will. From those, we have 2 nodes that are visible here, NS1 and NS4. And this is how fast we can filter on that data. Not only that, we can show things with which basically refused, apply that, and again, it filters that quick. I can do then, for instance, anything that's request for an address, apply that, and again, it's very, very quickly. Now, what I've just done here is actually visualizing a botnet. You might not know this botnet. This botnet is called Cutwheel, and Cutwheel happens to have his own resolver. So you won't see it in the ISP level, because it sends queries directly to an authoritative server. We happen to run one for UK, and so we see those. Now this is very interesting. This little resolver is fairly broken. I've only shown you a very small part of the brokenness. It is more broken than we show you now. But the cool thing that you can do with it, if you select a single dot, and then, for instance, go to top N, and we can show you the top source IP addresses. I know I shouldn't do this live. I do this pretty quickly. A bunch of IP addresses will show up. Those are infected machines with Cutwheel. So the moment it's on the screen, that's about the same moment I'm going to delete it, because I don't want to call anyone out. At Nominet, we don't share this kind of data at all. So what we do sometimes is, if we have lists of infected machines, we try to solve those. We try to, how do you say it? We're not going to contact these individual machine owners, but we do share that data with folks who can actually do something about it. Look at Ray again. Ray's always very relaxed. Give it a second. Give it a minute. Anyway, while this is going, I'll go to the... Oh, there it is. So these are a bunch of IP addresses. We have some more information here as well. I'll just do quickly that. And, yeah. And I'm going to delete it again. Anyone recognize their own address? No one? Good, I was fast enough. Okay, so those were infected machines. This is just one single thing that we can show. Oh yeah, that one bind bug. DNS servers are fairly deterministic. Bind, for instance, can do a whole lot of things. It can do continuous signing. It can do dynamic update. It can resolve. It's basically a very, very, very nice piece of software that can do an awful lot of things. And I can also tell you it's very, very, very stable. I know about all the stories you've heard, and of course when you see a bind bug coming up, right, that is because a lot of work has been, it's deployed an awful lot, and a lot of work has been going on in order to make it safe. So this bind bug that I want to show you is from 2011. Bind is a fairly deterministic machine. For instance, we do not allow dynamic update. right, on our public name servers. It's actually a very, very bad idea to allow dynamic update on your public name servers. If you know about DNS, you know why, because you can actually basically update anyone else's DNS that way. So we do not allow it. So we shouldn't see any responses from our own servers related to dynamic update, right? That makes sense, doesn't it? So with this system, I can actually show you, if I'm going to clear the screen here, let's say NXRR set. Now, all the dots should disappear and gone, right? We never, so what I just selected, sorry, I'm going a little bit fast. R code, response code, that's the stuff we send back to individual clients. Response code NXRR set, we should never, ever, ever see this live, because we don't have the dynamic update deployed on our live servers. I need to go back several months, and this takes a while. We have to go back to 2011. Was it January? I think it was January. Okay. Oh yeah, I have to click on the date. There it is. There's one dot. Literally one packet in January 18, 2011, between 7 and 8 a.m. UTC, we saw one response coming from our servers. Now, we have captured that message, and when we tried to recreate that message, something went wrong. And this individual message that we captured does not crash bind. But because we are not very, very, very good programmers, well, I'm not a very, very good programmer. I made a small mistake and I happened to crash bind. And I immediately mentioned that. Sorry, I immediately mentioned that to ISC, and they solved that in the end. But it's a great way to understand the behavior of your own system. Let me see if I can show some other stuff. Yeah, today someone mentioned Cryptolocker. Cryptolocker happens to be Zeus basically. Cryptolocker happens to be a very, very bad piece of malware that happens to, I think it encrypts stuff on your local hard disk. It makes use of a DGA. A DGA is domain generating algorithm. It literally generates a domain randomly. So it takes a date, today's date, and hustles that up and generates a domain, and adds, for instance, co.uk or .info to it. Now, I happen to have one here. I can clear this again, go here. No, need to go to all the way back to 2015. I should have prepared this better. There you go. There I am. I can now filter on this individual domain by just doing that. And filter on that IQ name. And you can see here this individual Cryptolocker domain. Now, this just goes to show that you can actually find these DGA if you do really, really, really your best. We have some machine learning stuff on top of this. I can't show you that now, but we have some machine learning stuff on top of this. What you see now is basically a GUI using an API. We have some machine learning stuff also using that same API. It basically looks at peaks, if you will. All of a sudden, you see a peak in queue names or a peak in IP addresses coming through. IP addresses as those who query. If we see, I think, more than 4 or 5 standard deviations difference, then we will highlight that. This is one way to find DGAs. I just searched because I heard Cryptolocker today, and I thought I'd just fill this out. Again, just to show you how fast this is, another feature I haven't shown yet is, for instance, top queue names. These are, in this hour, in this random hour I just selected, I can select any other one. These are the top domain names that people request. Not people, that machines request. Now, when we started out doing this, we thought that we would see like a lot of well-known domains in our top 100 queue names. This is absolutely not the case. Most of the stuff you see are infrastructure domains. As you may know, a domain is hosted on a name server that has yet another name, like ns1.nic.uk, which happens to be our server. So pdns6.ultradns.co.uk is one of the name servers of UltraDNS that they use to park a lot of domains on. That's why we see that high up in the list. And there's not much that we can influence in doing that. We can change our TTLs a little bit, but it is mostly the owner names, so the second or third level domain names that set their own TTL for their own servers. And that influences the frequency as well. We also have top IP addresses. There should be some well-known folks in there. Yep. Keep in mind that this is a little bit privacy related. Keep in mind that the bulk of the data that we see are from ISPs, resolvers, company resolvers. We don't see individual DNS requests because they mostly go to those resolvers and not directly to us. So the IP address that you see here, some of them are well known. If I do this, there are friends of OVH again with IPv6. There is Google again. The Google addresses that you see are basically the unicast backend to their Anycast 8.8.8.8 front end. Google consumes quite a lot of I can actually sort this, I think, or collate this by, where are we? By ASN number, and there we are. Google by far almost an order larger than the rest. Remember, OVH is doing something nasty, and one and all the rest are basically your basic mobile DNS providers, etc., etc. Sorry, your mobile network providers. I see Michael Daly up there laughing. Like, what is he talking about? Anyway. I just noticed I've got about 5 minutes left. I want to stop here and open up for questions.
Got 5 minutes plus questions.
Oh, I got 5 minutes plus questions. Okay, you're going to suffer 5 minutes more of me. Okay. Well, just think about the beer. It'll only taste better. One feature I haven't shown yet is what we sometimes use as well. Let me just see if I clear the filter. We can actually show individual packets as well. Now, also just a heads up, we can't control what people are asking for, so some very, 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 very bad domain names might come up. Also, this window is, even though I've selected about an hour's worth of traffic, this window only shows 9 seconds because that's the amount of dots I can fit on the screen. Each individual dot is a DNS request plus response. We can color it by different types. So this is by response type. You can have a delegation. You can have an NX domain that is cached. We don't have those because we're authoritative servers. No data, simple answers, empty answers, etc., etc. I can select each individual dot. Like I said, I have to watch out what I select. I can't see beforehand what domain I select. So this happens to be a benign one. 7oaksoundandvision.co.uk. If you actually type that into your browser now, I can see that in a minute. So don't.
But only if it's a cache miss.
Only if it's a cache miss. Well presented. So ask for hinfo or something, or another type that's very, very obscure. Anyway, you want to show you how fast this system is. Of course, what just happened is all of these, let's say about 100,000 packets are now in the front end. So I can show all of those. I'm going to go quickly over it. But interestingly, what I can show is, for instance, again, the behavior of our own system. Michael, who's our head of SAs, is here today. So hopefully I'm not going to call him out by showing latency in our systems. There's a fundamental difference in DNS between, and we found this out using this tool, and I'm pretty enthusiastic about this. You can only be enthusiastic about it if you're a DNS geek like me. So here's the thing. There's a fundamental difference between not responding and responding very, 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 very slow. So here's what happens when you not respond in DNS. These clients, these resolvers, will get very aggressive. They're like junkies not getting their drugs. Right? They get very, very aggressive. They hammer you to death. Right? You see massive amount of bursts, massive amount of spikes. However, if one of your name servers is basically very, very slow but still responds, right? Bind and a lot of other name servers are actually very, very nice to you. Ooh, you must be under a lot of load. Ooh, you're kind of slow. Let's find a faster name server first. And of course, until all name servers are exhausted, if everyone responds slow, or not at all, it's going to hammer the system again. So, so what I'm doing right here is showing you the latency in our system. This is combined NS1 and NS4, and I'm going to remove the timeouts, because there's sometimes a reason why we don't respond to packets. This has to do with bogons and things. But here we see latency in our system. Blue is good, and this is a whole heat map. You see it on your left-hand side here. All the way up to red. Red is really bad. It's more than a second's worth of delay. Now, there's a good reason sometimes we have that delay, because bind is doing other stuff, like logging or incremental zone transfer. Now, this doesn't mean that our system is slow. We color it red because one packet is slow, right? But keep in mind we have 2, 3 systems behind a single name server, if that makes any sense. So even though this one individual DNS response has been a little bit slow, all the other name servers are still very, very fast and working. Anyway, I think I'm kind of exhausted, and I want my beer. So, and if you guys have any questions, then let's have them now. Ray, if I forgot to tell anything, then just...
So if you want to grab any questions, we'll grab Roy on the afterwards.
Yep. As I said before, we're not sharing any data, so you can't talk to us about the data, if that makes any sense. I want to say that now out loud. I don't want people to get the wrong idea that we do anything with the data. At Nominet, we use this tool on a daily basis to find things like botnets, to clean up our own zone file, to find things like malware, misconfigurations. An interesting misconfiguration, or an interesting bug, if you will, from Google. This is actually fascinating if you know a little bit about DNS. So domain names can actually be as long as you want, right? They can be longer than 255. Technically, there's no restriction. Of course, the protocol says a domain name can only be 255 characters or less. But remember this, a domain name is basically a bunch of labels. And an individual label is about, I think, 63 characters long. But you can concatenate a bunch of labels, all the way up to however long it fits in a UDP message, which I think is about 64K. So, when Google started doing their 8.8.8.8, they invented a clever thing. They prepend a nonce before the domain name they're querying for. So it would be like quirkyrandom.example.co.uk that they ask for. However, they still have to distinguish between a wildcard domain, right, a domain with a wildcard prepended for it, and a regular domain. So if you would answer instead with a delegation with an actual response, what they would do is, okay, let's add another nonce, and add another nonce. And there's a loop here where they keep on adding nonces until the domain name was longer than 255 bytes. So what Bind did at the time was sending back a surfill for a domain name that's longer than 255 bytes. I think it's encoded somewhere. I think it's somewhere written down in some RFC. The problem is if you send back surfill, that means a temporary failure, and Google would go to the next name server responsible for the UK domain, which is yet another bind server, which will respond with surfill, which causes Google to go to the next server. And you get this massive loop and fantastic bursts. Basically, you get a very, very sharp spike of data that suppresses all the other data within that hour. And we mentioned this to Google. We fixed that problem. We've mentioned this to ISC. Next version fixes it. But those are the interesting things you can see with this kind of software. Anyway, thank you. Any questions?
Hi, Roy. Jim Reed. One question is, how much data are you actually accumulating in this system every day? I mean, are you capturing essentially all of the DNS traffic and responses for each server that's going into the system? How much data does that constitute on a daily basis? And how long do you plan to keep it for?
Okay. We get over all the system between 3 and 5 billion DNS requests. We capture data on 2 of the systems, and we call it a prototype is for internal use only. That said, I don't know in terms of gigabytes, but maybe Ray can do a query. Sorry? Yeah, a daily. Jim asked for a daily figure.
Give me 1 second while I search and find out.
So for how long do we keep it for? Not that long. That's the official answer while the microphone is open and the whole world can hear it. There's a fundamental difference in accumulated counts and the actual source IP address, domain name that they ask for, etc., etc. There's a legal limit as well in the UK. I think there's a legal limit in Europe, but technically you can store it as long as you want. You just add disk.
The legal limit is increasing.
Well,
So-
yeah.
Sorry.
I'm not a lawyer, so I'm not going to get involved in that discussion.
Yeah,
but I
sorry.
understand the question.
Yeah, I can't get in on the VPN from here. The system doesn't record any of the response data, so we can't tell what answers were given. We also don't consider that any of this is PII, because ultimately the thing that are hitting us are generally ISP recursive resolvers, not end users. But yeah, we do have something in the order now of 40 terabytes of underlying data collecting. Yeah, I think a few tens of it's trying to remember now. It's 50, 60 gigabytes a day, something like that, as a guess. I'd need to look into that, but I can't do it from here. And there's a MariaDB backend store in which all of these traffic volume graphs are generated that's hitting about 800 gigabytes.
Thank you, Ray.
Okay, any other questions for Roy and team?
That was an easy crowd.
Thank you very much, Roy. Cool
Thank you.
stuff.
Thank you.